So good afternoon, everybody. I'm Kim Budil. I'm the director of Lawrence Livermore National Lab, and I'm very excited to be here. This is one of my favorite events of the year, although I don't always get to come and participate in the meeting. I have been involved with the SSGF since its inception, so I'm particularly devoted to this. So thank you all for all the great work that you do and for all the great work you will do in support of our important laboratories and missions and science areas that we care about. I'm really excited to be here today to introduce this topic and to introduce you to my colleague, Tom Mason. But I'll start just with briefly setting the context for why this is an important topic for you to be thinking about. So when I first joined the lab system in a long time ago, 1987, the end of the Cold War, things were changing very rapidly in the US and in the national nuclear security enterprise in particular. So when I joined the lab, the Soviet Union still existed, as an example. So in the next 5 years, the Soviet Union would fall, peace would break out, an entirely new environment for cooperation between Russia and our country would emerge, and the country was embarking on what we imagined would be a peace dividend. And so in the mid-1990s, the Clinton administration launched the Stockpile Stewardship Program as an attempt to ensure that we would always have the ability to ensure a safe, secure, and reliable nuclear deterrent without further nuclear testing. The nuclear test moratorium was entered into in 1992 as part of that agreement, and the period before the launch of the Stockpile Stewardship Program was really a very difficult era for the laboratories. Budgets were extrapolated to zero in that period before stewardship was conceived. So we embarked on this really exciting program to build science and technology capabilities to steward the stockpile. We began real cooperation with Russians, including with the Russian nuclear labs, to ensure that they could turn their economy to peaceful purposes. And we sort of expected this, era of global cooperation and stability to last for a very long time. So fast forward 30 years ahead, where do we find ourselves today? We're in an environment of unprecedented global instability. We have Russia returning to an aggressive posture and seeking to assert dominance, invading Ukraine, threatening the use of nuclear weapons against a non-nuclear armed state, which is something I never thought I would see in my lifetime. We have China rising, not just to be an economic competitor to the United States, but to be seeking to be a significant player in the national security stage, including making significant investments in their nuclear capabilities. So we find ourselves not just in a world of strategic competition, but in a tripolar world, something we've never faced before. So a really very complex national security environment and economic environment. So there has been a huge focus in the government over the last number of years on how the US can remain competitive in this environment. And that's put a focus on the participation of foreign-born scientists in our research institutions, in our participation in the international science and technology community, and on how the laboratories can balance the obvious benefits of engaging in international science and technology and working with the very best scientists from around the world with the very real concerns about ensuring the US maintains leadership in strategic areas and receives the economic benefits of the investments we make in our own R&D ecosystem. So for about the last year, the national lab directors have spent an enormous amount of time and energy working with folks on Capitol Hill to help them understand what this risk calculus is, what is the benefit and what is the downside. So Tom's been a leader for us in this endeavor. Tom's the director of Los Alamos National Laboratory. He has the distinction of being one of only 4 people who served as director of 2 national labs. He just pointed out that he's ambidextrous. He's the only one of the 4 who's led an Office of Science laboratory, Oak Ridge National Lab, and an NNSA lab, Los Alamos. For the record, he also said NNSA is more complicated, so. Prior to taking on this role at Los Alamos, Tom was at Budil as their Global Laboratory Operations Senior Vice President and has a long and storied history in science and technology to bring to bear here, and is sort of the maybe unofficial historian of the NLDC, and social director. So you can ask him about that in the question and answer session. So I'm excited to let you hear Tom's view on the research security environment and how we arrived at this place and how we can find a better way forward. Tom.
Okay, well, thank you very much for that introduction and kind of setting the context for why there's a lot of discussion going on really around the country, and actually it turns out around the world. Last week, I spent 2 days in Ottawa at a Five Eyes meeting about research security that was talking about, common challenges faced across that group of like-minded nations. So it's not just a US conversation that's happening now. And as Kim said, I kind of take an interest sometimes in how we got here. And in the research security world, there's an interesting story of how we got here. This is not a new discussion. So I think the first important thing to understand when we're talking about research security, first off, we're not talking about classified research. That is classified. We do not share it with people from other countries, with very limited exceptions, like our colleagues from the UK. And someone trying to gain access to it, that's called espionage. And we have counterintelligence, and we have law enforcement, and so that's not what we're talking about when we're talking about research security. What we're talking about is fundamental research that will be published in the open literature. So sooner or later, anyone with a library card is going to have access to it. But nevertheless, there are concerns that privileged access to that pre-publication information can confer advantages, and if it's done in a nefarious way, can do so in ways that are kind of inappropriate. So we're talking about the security, what's the appropriate degree of a security around government-funded fundamental research. So the first thing to note is actually the whole idea that the government would fund fundamental research is a relatively recent invention. Prior to the Second World War, there was very limited government investment in fundamental research anywhere in the world. It was kind of more of a hobby for the wealthy, required support from a patron. If you read Galileo's treatise, he's always very careful to acknowledge his patron who paid for the work. And there were some universities, Oxford and Cambridge, that had enough wealth that they could sort of indulge people to do research. There were some exceptions. The military did sometimes fund R&D. Famous example is the Royal Navy's longitude competition, which led to the development of accurate clocks so that the Navy could figure out where they were. You'll note that's a pretty translational kind of research. It's not that fundamental. It's making a clock that's accurate. The Army was an early Wright brothers customer. I think the first Wright brothers customer in 1909, but actually did not pay for the development of the plane. The Wright brothers did that on their own nickel. And the government was willing to buy a plane once it had demonstrated that it could fly for a certain distance at a certain speed. So all the R&D that led to that was, I guess, what we'd call now venture funded or angel funded. The Morrill Act established the land-grant universities. That was at the end of the 19th century, and provided support for agricultural R&D. So that was certainly government resources that were going into research. But again, it was very translational. It wasn't at that time really research that developed new understanding of plant biology. It was more about helping farmers, get more yield for their crops, using the body of knowledge that existed by other means. So the focus, was definitely the application of knowledge as opposed to the creation of new knowledge. So what changed with the Second World War? So one of the things that changed was there was this thing created called the Office of Scientific Research and Development, OSRD. It was established by executive order in December 1941, so immediately after the Pearl Harbor attack. It had actually been in the works for about 6 months prior to that. The federal government sort of knew that we were headed into a war, and there was an interest in setting up an office that would coordinate wartime military R&D, predominantly in the universities. And then when Pearl Harbor happened, that was the impetus to get the executive order signed. It was led by this fellow here, Vannevar Bush from MIT and the Carnegie Institution. And under the auspices of the OSRD, there was research that led to the development of radar, proximity fuses, and the initial phase of the atomic bomb effort. Many other things as well, but arguably radar and the atomic bomb were the two most decisive examples of federal investments in rapid technological innovation that had pivotal impact on the course of the war. Radar really was what allowed Britain to survive the Battle of Britain. And of course, the atomic bomb ultimately ended the war in the Pacific. So the S1 Executive Committee, as it was called, was responsible for the atomic bomb effort prior to the establishment of the Manhattan Project. It was the most closely held OSRD activity. Outside of that small committee, no one else in the military or in OSRD was even aware that this work was going on. This was in contrast to the radar work, which was done very closely integrated with the Department of Defense, or actually the War Department as it was called then, and was more widely known, at least within the sort of defense circles. The interesting thing in terms of research security is up until OSRD was established, there had been research going on into fission. Fission was discovered it was explained in November of 1938. Lies Meitner and Frisch explained an observation. It had actually probably been discovered by Fermi several years before, but he didn't have good enough radiochemistry. In November of 1938, the fission explanation for what was going on in uranium was first published. And in January of 1939, Niels Bohr traveled to Washington, D.C. to give a talk at the American Physical Society meeting where he announced this result. And pretty much any competent practicing physicist at that time, on hearing that uranium was fissioning and neutrons were produced, which could then induce more fissions, and knowing the mass defect and E equals mc squared, could pretty quickly do a calculation that would say, oh my gosh, there's large amounts of energy associated with this reaction, and because neutrons are being produced in the reaction, there's the possibility that there could be a chain reaction, and therefore a bomb. So Fermi, who's sort of in the bottom left-hand corner, had fairly recently fled fascism in Europe. His wife was Jewish, and it was not a good place for anyone who was Jewish at that time. In this case, it was in Mussolini's Italy. Got together with people like Wigner and some of the other refugee scientists, and they made a proposal that people would voluntarily refrain from publishing in this area because they were concerned that advances that were published in the open literature would be available to Nazi Germany and might assist them in developing a weapon. So there was a kind of voluntary arrangement amongst the physics community to refrain from publishing that actually held for a while, mainly in the US and in Britain. However, apparently the impulse to do the right thing to prevent enemy from getting hold of weapons of mass destruction came into conflict with the impulse to not have a competitor publish first, because Frederick Joliot-Curie continued to publish. And once the physicists saw that he was publishing, they said, well, wait a minute now. He's going to get credit for all of these discoveries if we're not publishing. So that initial attempt kind of fell apart. But once OSRD was created and started funding the research, then it changed, because with the money came the string that was attached, which is this is going to be classified. So at that point in time, it sort of shifted from the fundamental research that you might have concerns about to, no, this is actually classified. And we're going to have counterintelligence officers and military security and all those sorts of things. So it sort of shifted from being a research security topic into more of a classification thing. So the Manhattan Project was created in August of 1942. Then Colonel Leslie Groves, promoted to general, associated with the formation of the Manhattan Project, took over from OSRD. So under OSRD, this had been a more or less collaborative research effort, largely conducted in universities, in places like the University of Chicago and Columbia and Berkeley and so on. People were kind of coordinating their efforts, and you do this, well, I got a, you know, I have a cyclotron, I can make some isotopes, I can do some cross-section measurements. And in 1942, it was decided, largely because of an influential British report called the Maud Report that actually said this thing could actually work, to shift gears from an R&D effort into, no, for real, this is going to be a crash program, we're going to make an investment to try and build a bomb to end the war. And so OSRD moved out of the picture, and the Army Corps of Engineers under Groves came in. The work continued to be closely held, just as it was in the S1 committee. There was very limited access on the part of the military, the administration, and Congress. In fact, it's been argued in this book here, which I recommend to you. It's a great history of nuclear secrecy called Restricted Data, that Groves was concerned about the implications of federal oversight in the event that it didn't work, and $2 billion, which in those days was a lot of money, was spent on something that didn't work. And in fact, interestingly, there was an effort to have congressional hearings to look into the massive boondoggle of expenditures that was going on in eastern Washington state, and the Senate was getting ready to convene a special hearing. They were all going to travel out there, and Truman, who was then a senator, this was before he became vice president, was on his way out there, and actually there had to be an intervention from the president to shut down the hearings because they did not want Congress to find out what was going on in eastern Washington state, where they were building the graphite reactors to make the plutonium. So it was very tightly held. Now, within the project, there was a lot of debate about sharing of information. In fact, one of the reasons that Los Alamos was selected as a site was because Oppenheimer, well, first off, he went there as a kid and liked New Mexico, but secondly, he wanted a location where they could basically sequester all the scientists behind a very high fence and allow them to debate freely without compartmentalization. Because he had a strong feeling this is a tough problem. The only way we're going to solve it is if we can freely share information and debate and argue, and if it's compartmentalized, it won't be successful. Therefore, let's just go somewhere where we manage security by isolation, basically. And following the war, this separate system of classification, keeping it separate from the rest of national security information, was actually codified legislatively in the Atomic Energy Act of 1948, which created this designation called restricted data, which is completely different from all other classified information. Most national security information, there has to be a proactive decision, oh, this is important to keep secret, we are going to classify it. With restricted data, because of its topic, it's born classified. So anything to do with nuclear weapons is basically classified, and you have to take a proactive declassification step in order to release it. In fact, initially in 1946, anything nuclear, even things related to medical isotopes or nuclear power, was considered restricted data. And that kind of gave birth to the whole system of classification. Prior to 1946 and the Atomic Energy Act, there were military secrets. They generally had to do with things like troop movements and so forth. But this created restricted data, and of course, eventually we began to get these other categories of national security information and secret compartmentalized information and special access programs and a whole kind of alphabet soup of classification, but that's all post-war. So At the end of the war, Vannevar Bush wrote this report for the president based on the OSRD experience. It's called The Endless Frontier. And it made the case that, and this is a sort of a quote of it's title of one of the sections, "Science is a proper concern of government," and also made the case that you need to preserve freedom of inquiry. So what Bush noted was that with things like radar, which, you know, not long before had been Maxwell's equations, completely fundamental research. In fact, Faraday was asked by the then Chancellor of the Exchequer, who eventually became the Prime Minister, what is the use of all this electricity stuff? And he reportedly said, well, I don't know, but I bet one day you'll tax it, because the Chancellor of the Exchequer, you know, is responsible for taxation. And so Bush made the case, okay, with radar, which had been Maxwell's equations, and fission, recall 1938, fission was discovered. 1945, a bomb was dropped. Remarkably short time frame. The neutron was only discovered in 1932. So there'd been this pretty rapid transition of pretty fundamental esoteric research into something of consequence for national security. And he recognized that there were big potential economic implications of this new science. There was a lot of interest in the potential for civilian nuclear power and the promise of medical isotopes. So he made the case that science is a proper concern of government. Lots of recommendations in the report. One was prompt lifting of security restrictions on wartime research to allow transfer to industry because of the possibility for nuclear power. And in fact, the Manhattan Project scientists were permitted to publish some of their results. There was an American Physical Society in 1946 where the floodgates opened. Not everything was published. You still had to get an approval, but the goal was to start to move this into the hands of industry. Also recommended a program to educate returning GIs. It's an interesting exercise to count the number of Nobel Prizes won by people who were the recipients of GI Bill funding. One could argue this is a precursor for the current program that we're here today recognizing in a certain sense. It was a talent acquisition program, not a malign foreign talent acquisition program, but nevertheless. And the establishment of robust government funding for basic research, for fundamental research that led to the National Science Foundation and the national labs. All that was laid out in this Endless Frontier report. And you could argue that actually this was the basis of the blueprint that ultimately led to the US prevailing in the Cold War. And it's the combination of the economic power that was unleashed by technological innovation and the impact it had on our military technology and military might. That was ultimately, as those two factors working together led to the demise of the Soviet Union and the events that Kim described that happened in the 90s following that. So with 1946, with the Atomic Energy Act, you now had this designation, okay, there's a set of things that are classified, but we do want to translate those results, get them published as quickly as possible so industry can do something with them. This sort of accelerated in 1953. Eisenhower, there shown at the UN, giving a speech, gave a famous speech called the Atoms for Peace that actually said, okay, we ought to be sharing more of the peaceful applications associated with nuclear R&D, peaceful uses. Now, to be honest, this was an overt power play by the US to say, we have this technology that is, we are the world leaders in, and if you, rest of the world, want access to that kind of expertise and the economic potential associated with it, then by all means, join our team. So it was an effort to project US power through technological dominance, basically. So he gave the speech in 1953, and in 1954, the Atomic Energy Act was amended to allow the sharing of non-military aspects of nuclear science, principally isotopes for medical and industrial purposes, and nuclear energy. And this was, as I said, this was designed to accelerate innovation, position the US on the global stage. Ultimately, it sort of became a step along the path to the establishment of the International Atomic Energy Agency. the Nuclear Nonproliferation Treaty, and export controls as a means of managing the fact that a lot of the technologies that are useful for, say, nuclear energy do have potential military applications. So this created a kind of a different space in between the fundamental research, where you're going to publish and share everything, and the classified stuff that was still classified under the Amended Atomic Energy Act that had to do with military applications. There was this sort of in-between space where you were kind of concerned of dual use, things could be used in a bad way, so you're going to create this regime of export controls to kind of manage it. It's not classified, but we're going to be careful who we share it with. And we have to get licenses to share the information and that sort of thing. So that was in the mid-50s. So by the early 80s, there had begun to be concerns about US competitiveness. The big wake-up call that happened somewhere between, I don't know, 1975 and the early 80s was that Japan was making cars that were cheaper and better quality and more reliable and better to drive than American cars. And, you know, Japanese consumer electronics. And so there was a big concern that primarily from Japan, but to a lesser extent from Germany, from our other wartime adversary, that had been developing technologically and economically and starting to pose a competitive threat. So that was part of the context. The other thing was that there was concerns about Soviet Union or East Bloc efforts to access US technology, first off by good old-fashioned espionage, which there was a long history of, but also by going the route of research activities that were not classified, but were close to areas of interest. And so, you know, the method of dealing with this was kind of ad hoc at the time. Defense Department funded then and funds now a lot of research in universities. Individual program managers would make up their own restrictions on how did you have to treat this funding, how open could you be, and so forth. So this was causing a lot of consternation. And so there was some legislative and policy responses. The legislative responses were two acts of Congress in 1980, the Budil Act and the Stevenson-Wadler Act. They were intended to foster the transfer of federally funded R&D to the private sector. So the response to the competitive pressures from Japan and other places was go faster. Federal government is funding all this research in the universities. We need to get it into the hands of industry. Let's set up a legal framework where industries and, where universities and faculty members are incentivized to do tech transfer because they might get a financial return through licensing fees and so forth. That's what's the essence of the Budil Act. So that was one piece of the response, was actually more sharing, easier sharing, basically, to accelerate innovation. And this was reinforced by something that was issued in September of 1985 called NSDD 189, National Security Directive, signed by President Reagan, and that stated, it's the policy of this administration to the maximum extent possible the products of fundamental research remain unrestricted. And fundamental research was defined as basic and applied research that was going to be published in the open literature. So it's not just what you might call basic research, supernova explosions. It's also applied R&D, but it's applied R&D that's not protected by, say, patents. It's going to be published in the open literature. This came about through a pretty intense debate. There were certainly strong voices at the time that were arguing for more restriction. And the Reagan administration came down on the side, actually, of no. Our competitive edge is innovation, go faster. So you had both the legal framework with things like Budil, and then you had this policy framework that said, in theory, the only dividing line ought to be the red line of classification. If it's classified, we're not going to share it. If it's not classified, share it as freely as possible, innovate as fast as you can. And then there's a little bit of an asterisk because, oh, by the way, there's export controls, there's proprietary information. So there's certain things that under statute are not classified but can't be freely shared. And that's actually recognized in this NSDD 189. And that's been the governing framework up until very recently, where Congress had started weighing in again with things like the CHIPS and Science Act. So post-Cold War, so the Cold War, as I said, ended largely due to the strength and technological sophistication of the US and our allies, and the strength of our defense, and again, and our allies through NATO. I would argue the endless frontier prevailed. Our open innovation model, where we, at the fundamental stages of research, shared and collaborated and moved fast, and then we had a framework to transfer that technology to industry so that industry could turn it into either weapon systems or consumer products, grew our economy and grew our military to the point where the Soviet Union just basically gave up. And the assumption, I think, was at the end of the Cold War, this is the tear down the wall speech, was that the world would adopt our blueprint. After all, we prevailed. It was clearly superior. The Soviet-controlled economy 5-year plan, model was not successful. In fact, when the Soviet Union fell apart, it was revealed to be even less successful than we had thought because we believed their brochures. And that was our rule book. So if the world adopted our rule book, then we ought to do just fine. We were headed into a world of rapid innovation, globalization, the flat world that's described in Tom Friedman's books. And economic liberalization would ultimately lead to democratization. So countries like the Russian Federation that came out of the Soviet Union were sort of somewhat certainly moving to try and build their economies and seemingly moving to be more open democratic societies. And China had a policy of peaceful rise, and we felt like, okay, they're not completely democratic now, but a little dose of capitalism and they'll be voting. So that was the sort of prevailing thought for about 30 years. And around 2010, things began to change. Russia began to systematically withdraw from and undermine the rules-based order. There was a famous speech given by Putin at the Munich Security Conference in 2007 where he basically explained what he was going to do. Everything he's been doing since then is completely consistent with that speech he gave in 2007. China also abandoned, and it was really probably 2012 when Xi Jinping came to power, the peaceful rise policy, which had been based on the idea that we don't want to do anything confrontational in the kind of military domain because that would compromise our effort to grow our economy based on engagement in commerce and manufacturing all the stuff that you buy in Walmart. And they had policies that started to get a little bit more aggressive. There's one called Made in China 2025 that sort of said, okay, we built our economy to a certain point, building stuff that was designed elsewhere, but when you buy the Apple computer that says, made in Shenzhen but designed in Cupertino, most of the economic value actually remains in Silicon Valley. And so China recognized this and said, we've got to start, making our own economic value rather than just getting a fraction of the value associated with manufacturing stuff designed elsewhere. So that led to a desire to really acquire a degree of technological sophistication and competence that had not been part of their early phases of their rise. Dramatic expansion and enhancement of military capabilities. I'm sure many of you have seen the open source reporting of all the hardened missile silos that are sort of sprouting up like weeds in the desert in China. The Belt and Road Initiative, which is trying to lock down supply chains globally. And then these things called the 1,000 talent programs, talent acquisition programs, to try and repatriate a lot of the people who come to places like the US and Europe to get educated and tended to stay here. And China needed them back if they were going to do the Made in China 2025 thing. So they established these talent acquisition programs to try and incentivize people to return. So you know, it's reasonable to ask the question, is this endless frontier model of government funds research, we collaborate and share openly, we transfer to industry, you know, the economy prospers, our military is strong, is that model fit for purpose in the 20th century? For the first half of the Cold War, at the end of the Second World War, when Vannevar Bush wrote that blueprint, and for the first 15 or 20 years after the war, the US was not just the largest economy, it was larger than everyone else put together. It wasn't just the largest R&D performer, it was larger than everyone else put together. So what that meant was, if there was some important new discovery, chances are it was going to be made in the US, or we were at least heavily involved in the inception of the idea and playing a leadership role in it, and it was going to be our industry that was going to be able to capitalize on it, because we were just bigger than everyone else. We didn't have to really think about industrial policy. We just got it because of sheer mass, basically. We get our fair share by default. And in the second half of the Cold War, of course, I mentioned in the 80s, with Japan getting a larger economy, and obviously Germany and the other European countries, they were starting to become more significant economically, but they were our partners and allies geopolitically. So, you know, although we might be nervous, about losing jobs to Japan, that was a big concern in the 1980s, they are our allies. It's not a fundamental threat to us. And part of the premise of globalization in the flat world was kind of rising tide floats all boats. You know, as they got richer, they were buying more of our stuff too. So it was you know, that was okay. That wasn't a threat. And in this post-Cold War period, the view was everyone's adopting our rules and way of doing business, so it'll all be good. And of course, we now face active military conflict in Europe involving Russia. China has been engaged in very aggressive technological and economic competition with very tight military integration. This sort of civil-military fusion is the kind of buzzword that's used to talk about that. And that doesn't, not even mentioning Hamas, Iran, North Korea, all the other things that keep us awake at night. So maybe the world we're in is different, and endless frontier is no longer fit for purpose. I think we ought to ask ourselves that question. We are trying to adjust to this changed environment, and I would say there's been some false, you know, some missteps in this process of adjustment and some course correction. The Department of Justice had this thing called the China Initiative. It did lead to some successful prosecutions. An example there is Charles Lieber, who was listed as a former Harvard chemistry professor, was convicted for making false statements and failing. You know, a good rule of thumb is if someone gives you an envelope full of $100 bills, think carefully. But while there were some successful prosecutions, there were also some pretty visible failures and some pretty poorly conceived efforts at prosecution, dealing with cases where, you know, there may have been bad behavior, there may have been misconduct, but that's not the same thing as breaking the law. And in some cases, there wasn't even misconduct, it was just a misunderstanding. So you had this mixture of things where there was real malfeasance all the way to, you know, cases where they just collapsed and caused, you know, huge harm to individuals who had done nothing wrong. So, you know, this process of trying to figure out how to adapt is not a straightforward one. At the end of the Trump administration, there was this thing called National Security Presidential Memorandum 33, NSPM 33, that was issued. There are not a lot of things that were initiated in the Trump administration that were continued in the Biden administration. Pick pretty much any area and you would say there were pretty big changes. In this case, that is not true. This thing came out under Trump, it's being implemented under the Biden administration, and it's you know, there's a continuity of effort on the part of the federal government. This is actually about the only topic the US Congress agrees on. When we meet with you know, senators and congressmen from both parties, they're kind of on the same page in terms of the competitive threat, particularly posed by China. but there are concerns about Russia and, as I mentioned, other countries as well. And you see that in the things like the Chips and Science Act, which actually includes provisions around this topic of research security. The research community went to Congress and said, okay, big competitive challenge associated with China. The solution is you need to give us lots of money. And Congress said, okay, we'll at least authorize, haven't totally appropriated yet, but at least authorize lots of money. But oh, by the way, research community that asked for all this money, how are you going to assure us that the US taxpayer who's paying for it is going to get the benefit of this investment? It's actually not an unreasonable question. So how to respond? This is a quote from some congressional testimony by Anna Puglisi, who was formerly the head of counterintelligence for the Office of the Director of the National Intelligence, head of counterintelligence for East Asia, so basically China. She's a China expert. She's studied this, written extensively about it. And what she said is extreme propositions such as closing our eyes, i.e. pretending there's not a problem, or closing our doors only benefit China. If we ignore what's going on with, and I'll give you some examples, then we're allowing our good ideas to be stolen, basically. On the other hand, if we shut the door, we're going to slow down innovation and ultimately we'll be overtaken. So it's important to carefully calibrate how we respond to this new and different challenge. I think the fundamental difference in terms of the competitive challenge with China, if you look at the case of Russia or even the Soviet Union previously, they're certainly military adversaries with a powerful military, maybe a little less powerful than we might have thought, but a very real nuclear deterrent. Economically and technologically, I'm not that worried, to be honest. I mean, they have capable people, they do smart things, but they can't take it to market. China, on the other hand, is a competitive challenge across all three dimensions: military, technological, and economic. And so, it's not something to be taken lightly. So another question, in addition to, and it sort of gets back to this, is the endless frontier model the right one, is does international engagement benefit US economic and national security? I would argue this is actually a reasonable question to ask. I mean, clearly we enjoy collaborating internationally. Have colleagues all over the world that I've worked with and published with, and who wouldn't want to go to a summer school in Sardinia on quantum decoherence? Absolutely, I'm all in. But the US government is not paying for my vacations. Is there an actual benefit to the US of international collaboration? Do we do better if we share, collaborate, educate, and host researchers from other countries? Or should we take stronger measures to limit access to US taxpayer-funded fundamental R&D? From my point of view, this is a dumb question. It's like saying, okay, in a game, whatever it is, football, basketball, hockey, pick your favorite sport. I don't know if synchronized swimming, the analogy probably falls down, but I don't think we call it synchronized swimming anymore. This is like asking, should we have a strong offense or a strong defense? You actually need both. It'll come back. There we go. So, as I said, it's not a question of whether or not we enjoy interacting with our colleagues or traveling the world. Is there concrete evidence to support the argument that benefits of international engagement, and there are some obvious ones. We pool resources. If you're tackling really big, expensive problems, maybe you ought to share the load. More minds on big problems, different perspectives. People come from different cultural backgrounds, different sorts of training. You're more likely to solve a complicated problem. Do those benefits outweigh the risks, which is we might lose our competitive advantage? Something that we discover may get commercialized in another country and lead to employment elsewhere, and then we wind up buying the stuff that the US taxpayer funded some of the fundamental research to enable. And of course, development of military technologies that could be used in weapon systems that are aimed against us. So I'm going to quickly go through a couple of case studies to try and make the case that this is true. The first two are kind of Los Alamos specific examples. But Kim could give you, I believe, many examples just like this. Not quite as cool as this one, though. So, Mars rover. For over a decade, researchers at Los Alamos, funded actually by NASA, have collaborated with colleagues at IRAP in France to develop instrumentation for the Mars rover. In particular, on the top of the rover, there's this thing called the SuperCam. That's the older Mars rover. The SuperCam, oh no, that's the new one. That's the new one. The first one was called the ChemCam on the first Mars rover, and the SuperCam is an upgraded version of it. It's the laser that zaps the rocks. And it uses a technique called laser-induced breakdown spectroscopy. And the first version of it, the ChemCam, could tell you at a distance what the chemical composition of that rock was, what the atomic composition, what species of the periodic table are present. The more recent version actually adds in Raman spectroscopy, so it'll tell you the chemistry as well as the elements. As a result of this work, and of course the reason you're doing that is you're trying to understand, has there been water on Mars? Were there conditions where life could have been created? Really interesting questions, as well as the geological history of the planet. So as with all kind of scientific collaborations, this has led to lots of joint publications. There's been exchanges of researchers. We had students at Los Alamos who went to France and did a postdoc and came back to the lab as permanent staff. And we've had researchers from France who've come to the lab. It has all the characteristics of a normal, healthy international research collaboration. And it's doing great science. However, it's also important to our national security. Why is it important to our national security? Well, why does Los Alamos do stuff in space and on Mars? There's two components to this. It's an important element of our strategy for both space and planetary science. It serves to attract scientists and engineers who may come in thinking, oh, NASA, Mars, very cool, and it's unclassified, so as a recently minted graduate, you don't need a security clearance to start working on it, but they have a skill set that's highly applicable to work that we do, for example, in collaboration with our colleagues at Sandia for the global nuclear burst detection system that's important for treaty verification and nuclear command and control. So all the GPS satellites have these packages that can detect a nuclear explosion anywhere on planet Earth, any time of day or night. And so this sort of skill base that we develop, partly through this very open international collaborative NASA work, has implications for very important closed, classified national security work, and it's many of the same people who come in initially on the open programs who then, over the course of their career, start to contribute in national security. On the planetary sciences, geology and geophysics is really important for understanding nuclear testing and compliance with the Comprehensive Test Ban Treaty. The bottom right-hand corner shows a picture from a New York Times article that came out in December talking about things that are being observed in Lop Nur, which is the Chinese version of, I don't know if north is this way, but whichever way the Nevada National Security Site is. And so satellite imagery has revealed lots of activity going on there. Guess what? The Chinese aren't really telling us what they're doing. We've been trying to be transparent, actually, about what we're doing at Nevada and taking non-governmental organizations, downhole to show them where we're doing subcritical experiments. Not so clear what the Chinese are doing. But the ability to understand propagation of seismic waves through different sorts of geology is one of the tools that we use to try and understand that. Or whenever North Korea makes the ground shake, what was happening. So again, pretty important national security stuff. It's built in this ecosystem where there's this open international collaboration. Final point on this is this LIBS tool, laser-induced breakdown spectroscopy, first deployed on Mars. Now that we've got it working in an easy environment on Mars, we're moving it into our plutonium facility, which is much tougher, it turns out, to help us with our PIT mission. So again, national security spin-offs associated with this open research. Second example, COVID-19. So this is a LA Times, Los Angeles Times, not Los Alamos Times, LA Times story from 2020 when Betty Korber and her colleagues published a paper showing that the spread of COVID-19 accelerated significantly by a new strain that emerged in Florence, Italy. It was more infectious than the original Wuhan strain. This was a hypothesis derived computationally. There's an international database called the Global Initiative for Sharing All Influenza Data, GSAID, into which researchers had been depositing the genomes, the sequences of influenza virus for many, many years. So when COVID happened, the infrastructure was already there, and people were sequencing COVID all around the world and putting the data into this GSAID repository. And so what Betty and her colleagues were able to do was extract that and demonstrate that a new strain emerged that very rapidly overtook the original Wuhan strain as the dominant strain. At the time this came out, this was incredibly controversial because it was basically computationally derived, and this is a field where people want to see the actual Petri dish study that shows that this virus has a higher rate of infection. And so there was a lot of skepticism that you could use this data analytics to derive something. But in any case, it turned out to be right, and of course we all learned about Omicron and all these other things. Well, it all goes back to this, and it was enabled by this global initiative, open sharing of all the genomic data. So that's another example, I think, and obviously there are national security implications associated with global pandemics. We all learned that. The final example is not a Los Alamos specific thing. It's looking at a whole ecosystem, artificial intelligence. Very hot topic right now. At the 2017 People's Congress, President Xi highlighted the importance of Chinese leadership in artificial intelligence and said, we have to lead in this field. And in fact, China has established leadership in some notable areas. They're probably better than any other place on facial recognition. Kind of useful if you're trying to keep an eye on what everyone's doing. So there was a 2023 study that was an update of a 2020 study that had largely the same conclusions by the Paulson Institute in Chicago looking at AI. What they did was AI, like many computational fields, the measure of quality is not peer-reviewed publications in archival journals because the field moves very, very quickly. So the real measure of quality is who gets the prestigious invited talks at the refereed conferences. And so what they did at the Paulson Institute, they looked at all the major conferences in the field and the individuals who got the prestigious refereed invited talks and where they're working, where they did their graduate studies, and where they did their undergraduate degree. So the first conclusion is that overall in AI R&D, the US leads. That was true in 2020. It's true in 2023. Lead has closed a little bit. China is catching up, but there's still US leadership position. The interesting thing, though, is shown in this chart on the right, and you can't read it, but basically the colored bars are different countries. So China is red, US is blue, India is this sort of blue-gray, Europe is purple. And it shows undergraduate degrees, graduate degrees, and full-time professional employment. And the full-time professional employment has fewer people because many of them are still in graduate school. Okay, so what's happening? Lots of people in China, many of them go to the US and other countries, Australia and so forth, to go to graduate school. Not many of them go back to China. Most of them stay in the US. So if you look at the share of undergraduates, the US takes a huge infusion of people in grad schools, and many of them stay. And it's about a 10-to-1 ratio, people who come here to get educated, who stay, compared to those who leave. So here's a very important area, and we have benefited significantly from an infusion of foreign talent, especially from China, but also from other countries. And that is why we have a leadership position. If you remove all those people, we do not have a leadership position. And I would argue this is important for economic and national security. This is a study that was done by DOE, AI for Science and Energy Security. Economically, a lot of the recent excitement, this is, sort of appears like it happened recently. In fact, it's been building for decades. But the recent excitement has been the generative AI models, and it's the US multinational tech sector that's been making all the headway here with things like OpenAI, Google DeepMind, and so forth. And you know, there's been lots of focus on the risks of AI, but there are very significant potential benefits for both economic and national security. So those 3 case studies are meant to say, yes, we do get benefit from international collaboration in all different forms, whether it's more at the PI to PI stuff like the Mars rover, all the way up to the whole ecosystem of AI and the migration of talent. And in fact, I would argue that the kind of counterpoint to that is what I would call the East German innovation model. So when the Berlin Wall fell, I was working in Denmark, had a lot of collaborators in Germany, from West Germany, who were all being sent to East Germany to go figure out what to do with the research institutes there. And there are a lot of pretty famous research institutes, famous on the basis of what they'd done, you know, decades prior, or even prior to the Second World War. They had great name brands, but when the West German colleagues began interacting with them, the way it was conveyed to me, they weren't surprised that they were behind. What surprised them is they didn't know how far behind they were. They were so disconnected with the rest of the world, they did not realize the capabilities that they lacked. And isolation hampered economic prosperity. I think it created the conditionals for technological surprise. One of the contributing factors to the demise of the Soviet Union was the Iraq War, when the Soviet generals saw that all those smart bombs actually worked. And they went, oh my God, we can't do that. They were surprised. And the reason they were surprised is because they had no engagement, really, because of the Iron Curtain. And reconstruction in East Germany meant creating entirely new greenfield research institutes. There wasn't much there to build on. So what's a more nuanced approach? I think this is my final slide. So I think actually NSDD 189, this Reagan-era thing that sort of said, basically, no restrictions on fundamental research, provides a good framework for rapid innovation while protecting what we need. No restrictions may be placed upon the conduct or reporting of federally funded fundamental research that has not received national security classification, except as provided in applicable statutes. So if it's really important to protect, classify it. If it's export controlled or proprietary information, we have ways of dealing with it. Otherwise, we ought to be engaging. So classify what we must, control through legal means, but don't restrict that which is destined for the open literature. You're going to be able to read it anyway if you get a library card. So what do we need to change? I do think we have to adapt with the risks associated with efforts to subvert the open research environment. We need to think through who we work with and on what topics. No researcher wants their ideas stolen, but the challenge here is it's not just a question of trusting an individual. So you may say, you know, I've known Kim for decades, I trust her, maybe you went to grad school together, or maybe, you know, they were a postdoc in your lab, you know they're good people. You have to understand they're working in a system that's placing expectations on them. They may have employment contracts that require them to extract intellectual property without disclosing it to you. And so it's not just a question of trusting the individual. You have to understand the institution, the system in which they're working. And that's something which, as individual researchers, we're not necessarily well equipped to do. So I have more slides, but I think I've talked for a long time. So I'm going to stop here, because we do have, I think, about half an hour for discussion. And it would be great to get some questions, and you can ask Kim questions too. So.